is becoming infinitely large in the positive or negative direction, and we're seeing what happens to the y values. So in that first example, and this you might want your graphing calculators for, if you want to do this kind of collectively in your groups, what I'd like you to do, just take a minute, 2 minutes here, and fill in the y values for this function for the x values I've given you. So it just says complete the tables for that function f of x, and it says round f of x to 6 decimal places if you get a decimal. And remember, you can arrow over in your table to like highlight a number and it'll show more decimal places. It's not going to automatically show you 6 decimal places. Careful with how you have these typed into have the function typed in your calculator. You'll need parentheses around the numerator and denominator. Yeah, because your calculator, the way you type it in, is going to follow order of operations. So, what do you notice between these two tables? Your y values, yes, are going to be the same. That should make sense if you're looking at it, because the x values are just the complete opposites of one another, and when you square x, it's going to be the same whether it's positive or negative. So just to maybe save you some time if you're substituting them in. All right, so I think I was just kind of making sure when I walked around that the values you were writing down seemed to be correct. And if they weren't, I talked to you about it. But check the values you had. And the main thing, I don't want to move too quickly, but this was just to get you to see what's happening here. In that first table, what would you say the x value is approaching? Infinity, it's getting larger and larger. I realize 1,000 in, retrospect of other numbers, it's not terribly large, but x values are getting larger and larger. So this is showing as your x values would be approaching infinity, so getting infinitely large, what would you say your function f of x is approaching? 1. And then from the other side, as x would approach numbers infinitely large but in the negative direction, our y values are approaching the same thing, so approaching 1. So it's looking at limits as your x values become infinitely large in either direction. And then what I also want to show you, and you could even, if you still have that typed into your y1, you could get this graph. This is what that would mean then on a graph. What's happening at the y value 1? It's an asymptote, but a horizontal asymptote. So yesterday, the infinite limits, if x was approaching a number and your y values were approaching positive or negative infinity, that meant there was a vertical asymptote. Here, if x is approaching positive or negative infinity, so you're looking at what's happening on the left and right ends of your graph, if y is approaching a specific number, that number is meant to be a horizontal asymptote. So for this function, the value y equals 1 is a horizontal asymptote. So kind of thinking ahead, we proved vertical asymptotes with our infinite limits yesterday. To prove horizontal asymptotes, we would use limits at infinity to prove that. So we'll get into that as well. Well, and the difference is how to work with a limit if your x values approach positive or negative infinity. So how to find a limit without making a table. Because if you think about it, you can't plug infinity in as a number. So here's the definition. I don't feel the need to read word for word through it, but this is what the notation is going to look like for these. So you're going to see your x is approaching either positive or negative infinity. And then if this limit does equal a number, L, we're going to see on the next page that number represents a horizontal asymptote, or y equals L would be a horizontal asymptote. But this shows geometric representations of horizontal asymptotes. What I want to point out to you is it's possible for a function to cross a horizontal asymptote. So notice in the first one, y equals L is considered a horizontal asymptote even though it's really only the asymptote on that one end, not on the leftmost end of the function. Here is maybe more of what we think of as a horizontal asymptote for the whole function. But then this one, it's very hard to see because, again, copying pictures doesn't always work out the best. This function actually crosses the horizontal asymptote numerous times. But you can see it's kind of oscillating less and less. So it is approaching that y value L. It would be a horizontal asymptote there. Why does it cross? That's just the nature of that function. I'm just pointing out that this is still considered an asymptote even though the function crosses it. Because sometimes we think of an asymptote as it's never touched at any point on the curve, and it can be crossed and still be considered an asymptote. Yes, because if you cross a vertical asymptote, like if this happened vertically, then it's not a function. Yes, yep. So typically they don't cross vertical asymptotes. So on the next slide is the actual definition of limits proving horizontal asymptotes. So the line y equals L is called a horizontal asymptote of the curve y equals f of x if either of these two limits is true. So when you check for a horizontal asymptote, there's only two limits you ever have to find, and that's the limit as x approaches positive infinity, does it actually approach a number, and then the limit as x approaches negative infinity, does the function actually approach a number. And so it could be like that first example we looked at where there's just one horizontal asymptote and in either direction towards positive or negative infinity you're approaching the same y value. You could have two separate horizontal asymptotes where in either direction your curve is approaching a different y value, as in the case of inverse tangent. So this here is the graph of inverse tangent, and notice that graph has two horizontal asymptotes. So we would say for this function that the limit as x approaches positive infinity of inverse tangent. So that's looking towards the right side of the graph. So as x is getting infinitely large in the positive direction, we see the y values approach positive pi over 2. So positive pi over 2, that line is a horizontal asymptote. And then the limit as x approaches negative infinity for inverse tangent of x. That would be looking at the leftmost part of the graph. X is getting infinitely large in the negative direction. That horizontal asymptote, or those y values approach negative pi halves. So it is possible to have two different horizontal asymptotes. I don't know what that was. All right, so here's what I would like to do. I would actually like to skip over this example. This was mainly looking at a graph. So finding the asymptotes on a graph, and then for the asymptotes, writing out what the limits would be, kind of tying in yesterday and today. And we can come back to it. But I want to make sure we get to the examples like in example 3. So before we get here, though, I do want to talk about what's in this box. So this is important. For any positive integer n, if you have the limit as x approaches positive infinity or negative infinity of 1 over x to any power n, positive integer, that limit will always be 0. The reason why, if you think about substituting in a very, very large number, like 1 over, say 1 over a million. All right, so that would be 1/1,000,000. That's a number that's really, really close to 0. So if you're substituting in very, very large numbers for x, your y values become close to 0 on either end. So we're going to use this to then evaluate limits at infinity of rational functions. So it says what we're going to do here, because if you think about it, we can't use direct substitution. You can't plug infinity in for x because infinity isn't a number. So to evaluate these limits, you first divide both the numerator and the denominator by the highest power of x that occurs in the denominator. And then we'll use this rule to evaluate the limit. So in example 3, we have evaluate the limit as x approaches infinity of, and you do this regardless of whether x is approaching positive or negative infinity. So of this function, so you pick the highest power in the denominator, which is x squared. So I'm just going to make a note. This isn't, I guess, correct notation. I'm going to divide all terms by x squared, dividing everything by x squared. So I'm going to rewrite the limit. I'll have the limit as x approaches infinity of, so if I divide 3x squared by x squared, I'll just have 3. Minus, if I divide x by x squared, I'll have 1 over x. I would have x over x squared, which simplifies to 1 over x. and then minus 2 divided by x squared, nothing cancels, so I would just have 2 over x squared, all over 5x squared over x squared, or divided by x squared, is just 5, plus 4x over x squared would simplify to 4 over x, plus, and then I would have 1 over x squared. And I'm allowed to do this algebraically because I'm dividing both the numerator and the denominator, everything by x squared, so technically this is equivalent to what I started with. But now I can use this rule combined with limit laws we've learned. Remember, when you take a limit, you're taking the limit of every single term in the numerator and the denominator. So when I take the limit as x approaches infinity of 3, the limit of a number is just itself, so that limit is just 3. The limit as x approaches infinity of 1 over x, I'm using this rule here, this approaches 0. 1 over x will approach 0. If I have 1 over something infinitely large, that'll be really close to 0. So that term approaches 0. 2 over x squared also approaches 0. Basically, any number over x to a power as x approaches infinity is approaching 0. So then I just have 3 in the numerator for my limit. And the denominator, limit of 5, will just be 5. 4 over x is going to approach 0. 1 over x squared will approach 0. So your limit is 3/5. Questions on that? Who came up with that? I don't know. Some mathematician. All right, and what this means, it doesn't ask us this, but so you kind of tie in the meaning of this. This means the line y equals 3/5 would be a horizontal asymptote. So it's not asking us that in this question, but just so you tie those ideas together when you're asked to find horizontal asymptotes, that's what that limit actually represents. Right, because remember the limit, what it's equal to, that's the y value it's approaching. So this is the y value. The x values are the numbers getting infinitely large. So it's saying if you graphed this function, if you looked way to the right on the curve, it would be approaching, or you'd get that asymptote at the value 3/5 or 0.6. Well, this is the asymptote. So that horizontal line, if you graphed it, would be an asymptote to that function. Yes. All right, so if we look at, well, would everybody be okay? I mean, 4 and 5, these are examples depending on how much time we have, I include more examples than maybe we need. Is everybody okay if we skip to 6? Okay, because 4 and 5 you would evaluate the same way. Even though 5 is approaching negative infinity, you work through it the same way. 6 just looks different. So here's how you'd work through 6. It'd be nice if we could write this as a rational function, or as a function that is a fraction. I guess it's not rational because of the square root. So I can think of this right now as being over 1. And what I'm allowed to do is I can multiply this by the conjugate of the top. So I can multiply by the square root of x squared plus 1, but then plus x, and do that on the top and the bottom. So then make sure you still write, I have the limit as x approaches infinity, because I haven't taken the limit yet. And now on the top, if I FOIL these, square root of x squared plus 1 times itself cancels out the square root, so it's just x squared plus 1. And then the two middle terms will cancel out because I'm multiplying by a positive x and then a negative x. And then I have negative x times positive x, so that's minus x squared. And on the bottom, I have the square root of x squared plus 1 plus x. So ultimately, on the top, the x squareds cancel out. I just have the limit as x approaches infinity of 1 over the square root of x squared plus 1 plus x. And, well, what do you think the value of this limit is? So, yeah, my top is approaching 1. That's all I have on the top. If I were to substitute in a very large number, I have that very large number squared plus 1 square root plus the large number. This is going to be huge. So it'll approach 0. Because I'm going to have 1 over something very, very large. And 1 over something very, very large is going to approach 0. Questions on that one? Okay. For 7, this I included the graph when, well, I'll say this. So we have the limit as x approaches negative infinity of e to the x. Looking at that graph, what is the value of that limit? 0. So if x is getting infinitely large in the negative direction, y equals 0 is a horizontal asymptote. That part of the curve is approaching the y value 0. You want to know what the graph of e to the x looks like. And this, I mean, it wouldn't even have to be e to the x. If it was 2 to the x or 3 to the x, this limit would be the exact same. So just knowing what an exponential curve would look like. All right, then let's talk about 9. I am going to come back up to 8, but 9 will be quicker. Limit as x approaches infinity of sine of x. Think of the graph of sine of x. What would that limit be? Think about that. What happens with the graph of sine of x? Yep, so it oscillates. It continually goes from -1 to 1 over and over again. So does it approach anything? No, so this doesn't exist. So all of you Mean Girls fans, if the limit never approaches anything, it doesn't exist. The limit doesn't exist. Sine of x doesn't approach anything. Mean Girls? Watch it. Yes. Yes. The movie ends with like a math competition. Yeah. She's a math lead. Yes. 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 We're not going to watch Mean Girls in class. I don't think that would be approved. All right. I do want to, I know we're at like the 1.5 minute mark here. If we look back up at 8, I just want to explain this. This is one of those composite functions. We have 1 over x substituted into the e to the x function. So here, here's what you have to think about. When you see this limit, this means you're really taking the limit as x approaches 0 from the left of 1 over x. So you're taking the limit of that inside function because it's a composite function. This is infinity. Well, so if we plug in 0, we get 1 over 0, which means it is either positive or negative infinity, because 1 over 0 doesn't exist. So the question is, which one is it? this is positive. If I'm approaching 0 from the left, this is negative, so it's negative infinity. So if the 1 over x is approaching negative infinity, now your limit is very similar to this one, where you're thinking if that's approaching negative infinity, what is e to the x approaching? So this limit is 0. So if the exponent approaches negative infinity, that's approaching 0. You're kind of thinking of it in two parts. All right, the practice is there out of the book. We'll go through questions if you have them tomorrow.